Thermodynamics. Study of the transformations of energy. Universe is equals to system plus surrounding. System is equals to object of study. Surrounding is equals to region outside the system. Boundary is equals to separating interface. Types of system and boundaries. Open system. Transfer of matter and energy through a permissible wall. Closed system. Transfer of energy through a diathermic wall. Isolated system. No transfer of matter and energy through an adiabatic wall. Work done when an object is moved against an opposing force. Energy. Capacity to do work. Heat. Energy transferred as a result of temperature difference. Thermodynamic laws. Zeroth law, thermal equilibrium. First law, conservation of energy. Second law, spontaneity of process. Third law, entropy of system at T is equals to 0. First law of thermodynamics. Internal energy, U. Total energy of a system. For an ideal gas, pressure multiplied by volume is equals to nRT, where N is equals to moles, R, gas constant, is equals to 8.314 joules over mole minus K, and temperature is equals to K, Kelvin. PV over T multiplied by A, is equal to PV over T multiplied by T, wherein P stands for pressure, and V stands for volume. Isolated system. Constant U, which stands for internal energy, delta U equals to 0. Q, which stands for the heat added to the system, is equals to 0. W, which stands for the work done by the system, is equals to 0. Closed system. Delta U is equals to Q, which heat added, plus W, which is through work done. Delta U is equals to Q. There is no work done. Delta U is equals to W. There is no heat transferred. For all the gases at constant volume, delta U is equals to the integral of CV, dt. Where CV is equals to heat capacity over moles, heat capacity / moles. For thermodynamics process. Isochoric process, dV is equals to 0, and dW is equals to 0. Isobaric process, dP is equals to 0. Isothermal process, dt is equals to 0, dV is equals to 0. Adiabatic process, dQ is equals to 0. For isothermal process, cancel delta U, and equate to 0. Then 0 is equal to Q plus W. Hence, Q is equal to negative W. Isothermal work. Work W, is equal to nRT lane of volume 2 over volume 1, where N equals moles, R, gas constant, is equals to 8.314 joules over mole minus K, and temperature is equals K, Kelvin. First law of thermodynamics sample problem. Calculate the work done for the isothermal, reversible expansion of 1 mole of an ideal gas at 25 degrees Celsius from 1.5 liter to 2.5 liters. Delta U is equals Q, heat added, plus W, work done. Cancel delta U, and equate to 0. Then 0 is equal to Q plus W. Hence, Q is equal to negative W. Next step, work W, is equal to nRT lane of volume 2 over volume 1, where N equals moles, R, gas constant, is equals to 8.314 joules over mole minus K, and temperature is equals K, Kelvin. W is equal to negative 1 mole multiplied by 8.314 joules over mole minus K, multiplied by the conversion of temperature, which is 25 degrees Celsius times 273.15 degree Kelvin, lane 2.5 liters over 1.5 liters. Which results to work, W, is equal to 1266.24 joules. Second law of thermodynamics. Entropy of an isolated system increases in the course of spontaneous change. Entropy, state function used to express the second law of thermodynamics. Spontaneity, things that happen naturally. Types of change. 1. Natural change, spontaneous, no work is applied. 2. Unnatural change non-spontaneous, work is applied. Physical statement. Kelvin statement. It is impossible to completely convert heat to work. Clausius statement. It is impossible to build a Carnot heat engine with only a heat reservoir. Thermodynamic efficiency of heat engine, E. E is equals W over Q multiplied by H. Equating the formula to QH minus QC, over QH. Then simplifying to 1 minus QC over QH. Where W is work done, Q is the heat content, H is the heat transfer, and C which is the specific heat. Sample problem. A heat engine takes in 900 joules of heat from a high temperature reservoir and produces 300 joules of work in each cycle. What is its efficiency? Efficiency, E is equals to W over QH. E is equals to 300 joules over 900 joules. The efficiency is equals 0.33. Carnot heat engine. E is equals Tc minus Th, over Th. Simplifying it to 1 minus Tc over Th. Sample problem. Water near the surface of a tropical ocean has a temperature of 298.2 degrees Kelvin, which approximates to 250 degrees Celsius, whereas the water, 700 meters beneath the surface has a temperature of 280.2 degrees Kelvin, which approximates to 7 degrees Celsius. It has been proposed that the warm water be used as the hot reservoir and the cool water as the cold reservoir of a heat engine. Find the maximum possible efficiency for such an engine. Solution. The formula, efficiency, E is equals to 1 minus Tc over Th. E is equals 1 minus 280.2 degrees Kelvin over 298.2 degrees Kelvin. Which results to efficiency, E is equals to 0.06. Carnot refrigerator. Internal work is equal to the hot transfer minus the cold transfer of heat. Coefficient of performance, COP, K. Ideal refrigerator, K is equal to Tc over Th minus Tc. Simplifying to Tc over Th, minus 1. Sample problem. A refrigerator uses 400 joules of work to remove 200 joules of heat from its contents. How much heat must it reject to its surroundings? Answer. The refrigerator must reject an amount of heat to the room equal to the sum of the work done by the refrigerator and the heat removed from its contents, or 400 joules plus 200 joules is equal to 600 joules. 200 joules is equal